Hi, welcome to Lesson 19C, Kinematics. The goal of today's lesson is to calculate the distance traveled and displacement of a particle given the velocity, or perhaps even given the acceleration. So, we've learned over the past little while that if we have a function, we can find what that function used to be before it was differentiated. And when we differentiate this, and actually sorry, this isn't equal, if we differentiate this uppercase f of x, that gives us lowercase f of x. Okay, so by integrating or taking the antiderivative of this, we get what that original function would have been. So that can be applied to any sort of function. So if I know the velocity function, then I can find the displacement function by taking the antiderivative of that. If I know the acceleration function, I can take the antiderivative of that to give me the velocity function. And then of course, once I know that, I can then take the antiderivative of the velocity function to give the displacement function. Okay. One of the things that we know, or what we may have learned in the past, is the distance, speed, time triangle. That can be handy for us when we're trying to find the distance, the speed, or the time. If we know a couple things, or basically if we're trying to find one thing, if we're trying to find the velocity, it's distance divided by time. If we want to find the time, it's distance divided by velocity. And of course, if we're trying to find the distance, it's the velocity times time. So, knowing that the integral of velocity is displacement, and we also know that velocity is, the integral is the area under the curve. Suppose we have a velocity time graph. Usually we use distance time, but this time we're going to use velocity time. And suppose, or speed time, whatever we want to look at this, and suppose there's a constant speed of, say, 80 kilometers an hour, and the object is moving for 2 hours. Then from this distance, speed, time triangle, if we want to know the distance, then we're going to find the velocity times the time. So the distance, and I'm changing that to speed because I'm not taking into account the direction at the moment. So its speed in this case is 80 kilometers per hour, and we're multiplying by 2 hours. And so we get 160. And notice also this is hours over 1. And so the hours and hours will cancel, so we're just left with kilometers. So the units also check out. Sorry, I missed all of that I was writing. So distance equals speed times time. The speed is 80 kilometers an hour. Time is 2 hours. And so this is hours over 1 is the units. So the hours in the numerator cancel with the hours in the denominator, which just leaves us with kilometers. So 80 times 2 is 160 kilometers. We can also look at this. So that was a geometric view of this. If we take a look at the definite integral from 0 to 2 of 80 dt, so this is the speed. We're integrating the speed. This is going to give us 80t evaluated from 0 to 2, and then when we just substitute that in, we got 80 times 2 minus 80 times 0, which gives us 160 kilometers, just as we saw earlier. Okay, so that's one application of that, of kinematics, and with a very basic function. What if we were to look at a function that's not quite as basic? Suppose we look at a function that's accelerating. So again, we've got the velocity time function, or velocity time graph, and we say it's accelerating up to 80 kilometers an hour, and that takes 5 minutes. 5 minutes, of course, if we're talking about 80 kilometers an hour, we want to keep the units equal or equivalent, so we'll use time in hours. So then that means that this 5 minutes, well, we know that there's 60 minutes in an hour, so 5 minutes divided by 60 minutes per hour is equal to 1/12 of an hour. Okay, so this is 1/12. So if the particle starts at rest, or the object starts at rest, that means it's going from 0 kilometers an hour up to 80 over 1/12 of an hour. Okay, so the average speed, well, it's 80 plus 0 divided by 2, so the average speed is going to be 40 kilometers an hour. And if we want to know now the distance, again using the distance speed time triangle, if we want to know the distance, we take the speed times the time, so we're going to have the distance equals 40 times 1/12, and that's going to give us 10/3 of a kilometer, which is 3 1/3 kilometers. Actually, sorry, it's exactly 3 1/3. It's approximately equal to 3.33 kilometers. If we look at this as area under curve, well, we see this is now as a geometric relationship here. We see we have a triangle, and so distance is going to be 1/2 the height, which is 80, multiplied by the base, which is 1/12. Well, 1/2 of 80 is just 40, times 1/12. Again, I'm doing it again, I'm sorry. And that's going to give us 10/3 kilometers, as we saw before. And then using the definite integral, we go from 0 to 1/12 of an hour. And so because we're doing distance times time, we need to find actually the equation of this line now in order to find the definite integral. And so if we're going to find that this speed here, the equation of this line, well, it's basically delta y over delta x. That's rise over run, or y step over x step. And so that's going to be, the gradient is going to be 80 divided by 1/12, which when you divide a number by a fraction, we get 960. In this case, we multiply by the reciprocal. So the equation of this is 960t. Okay, so just by using the gradient, the rate triangle for that. So then, to find the integral, we're finding the integral of 960t dt, and the integral of that is going to be 480t squared, evaluated from 0 to 1/12, and 480 1/12 squared minus 480 times 0 squared. So that's 480. Well, 1/12 is 1/144, so I can just multiply that in. So 480 divided by 144 minus 480 times 0, which is just 0, and then 480 over 144. That would be 40 over 12, which again gives us 10/3 of a kilometer.